Good morning. So today we're going to look at speed time graphs. The speed time graphs are slightly different to the distance time graphs you looked at last time. So as you can see on the graph here, I've got straight lines to start off with. We're going to look at curves afterwards. So we've got two formulas on the board today. Speed is distance divided by time, and acceleration is the change in speed over time. Because you can use both those formulas in conjunction with these sorts of graphs. So the first thing, we've got speed and time. We can use the speed time graphs to work out the distance. If you think of the formula, distance is speed times time. Now each one of these individual little squares, if I was on the grid here, would be a unit of distance. So to work out the actual distance travelled in this graph, what I need to find is the area of the graph, the area under the curve, or the straight lines in this place. So all I have to do here is split them up into the three obvious shapes. So I can see a triangle, a rectangle, and another triangle here. So by working out the area under the curve here, I will have a distance. So let's take the one at a time here. The width is 1 here, the height is 30, so that's 1 times 30 divided by 2, that's 15. This one, the width is 1, the height is 30, so that's 1 times 30 is 30. This one here, the width of it's 1, the height is 30, so that's the same as the first part. Add them together, comes to 60, and it's going to be 60 miles. The reason it's 60 miles and not 60 meters or 60 kilometers is because the units here are miles per hour on this axis and hours on this axis. Okay, so that's how you find the distance from the speed times graph when you've got straight lines. Now straight lines are easier to work with because the shapes are easier to work with. Give you an example of a curve now. So, same axes as before, speed and time. Times in hours here. So that curve there tells a story. Speeds up, slows down, speeds up again, and then slows down again. Okay? You could think of a context of that. That could be someone arriving at a roundabout, then going again, and then coming to a halt when they get back to their destination. Could be something like that. So we'll label this up. So we've got 0, 1, 2, 3, let's say 4 hours there. We'll get the distances in place as well. So we'll call that a top speed of 40, 30, 20 and 10. In order to work out the distance travelled here, again, is the area under the curve. The difficult thing here is that we're not going to be able to find it exactly because we've not got straight lines. So what I'm going to do is break it up into the most obvious shapes that I can make. Okay? So I'm going to break it up into the 4 strips, 1 for each hour. 1, 2, 3, and then 4 at the end there. Now I'm going to estimate the area of each of those strips. Now to do that, I'm going to try and make the best approximation of that shape as I can. So this first one here becomes a triangle for me. So that one would be, if we called that 24, 24 times 1 over 2 is 12. This next one, probably just about a trapezium. So you could break it up into a trapezium and a triangle if you wanted. So the easiest thing might be to do this. So for this part of the trapezium, you've got 1 times 24. And for the top part of the trapezium, you've got a height of 6, a width of 1, and it's a triangle. So that one comes to 27. The next one is a bit of an awkward shape. You may have been better to break that up into 2. We're usually asked in the question actually to break it into a certain number of strips. So for this question we're going to assume we've been asked to break it into 4 strips. Now this highlights actually the inaccuracies of this approach. It's the approach you're supposed to take, but it's still not perfect. It's the estimate. So if I take that path there, we've actually pretty much knocked off the top of that shape. But that's the problem with this method. It's not a problem for you guys, it's the method we're supposed to use, but it's a bit of a limitation. This is going to be a massive underestimate. So the height here we said was 30. So this is a rectangle. So it's just 30 times by 1 is 30. In theory it should be a trapezium, but actually the way the shape has panned out, it's ended up being a rectangle. And the last one's a triangle again. This time the height of the triangle is going to be 30, reading across. So that would be 30 times by the width over 2 is 15. So the distance under that curve will be my 12 plus my 27 for the second one, plus 30 for that one that didn't really work out very well, and plus the 15 on the end. So that gives me 39, 69, 79, 84, and it's going to be in miles, because again we're finding the distance. So those two little examples talked us through how to find the distance under the curve. Okay, the area under the curve is always the distance. This one didn't break down really nicely. Sometimes this fits really well. Sometimes you get an underestimate. Sometimes you get an overestimate. It's because we're trying to make a curvy shape into a straight line shape, and actually it's an approximation, and it's supposed to be an approximation. So the last thing to do with these graphs is to find the acceleration. Now acceleration is a rate of change, is how quickly things are speeding up or slowing down. So if I've got a speed time graph again, we're usually asked to estimate the acceleration at a certain point. The curve is deliberately a non-referenced curve there. Okay? Let's maybe tidy it up a little bit. I'll tidy up a little bit. There you go. The tidier it is, easiest to see. So if I want to find the acceleration this time, acceleration is the change in speed over time. If I wanted to find the acceleration at this point here, what I'd have to do is draw what's called a tangent. The tangent basically follows the shape of the curve as best as I can. With that tangent, I work out the gradient. So I work out the change in time and the change in speed. So the change in speed there, if I said that this point was 10, this point was 40, the change in speed would be 30. If I said that was 1 hour, that was an hour and a half, that was 2 hours, then the change in time there would be from 1 to 2, would be 1 hour. So that means the acceleration there would be 30 divided by 1, which is 30. Now, or miles per hour squared, or whatever the units you put in. We usually have seconds and meters here. Meters per second and meters and seconds. Because usually we're looking at projectiles and things like that on a smaller scale to the miles per hour, but you can have miles per hour there. So the 30 will be meters per second squared. Okay, now that is everything you need to know for speed time graphs. Okay, so use this when you're doing your task on MyMaths, and hopefully it'll be of use. Thank you.